Hey, physical geology students, I wanted to just wrap up with the part of the glaciers lecture that we didn't get to today in class. So the last 10 slides of the lecture, I just want to quickly go through and cover the material that those slides were intended to cover. The first is shows a picture of the globe with a big glacier on the northern hemisphere and a picture of the cuddly animals from Ice Age, the movie, and a guy named Louis Agassiz. Basically, the idea here is just that one of our most recent major geologic events on the planet Earth has been a period of sustained glaciation that's happened over the past about 2.5 to 2.1 million years or so. And we commonly refer to this as the Ice Age. It's not the first Ice Age the Earth has been through. It may not be the last Ice Age the Earth has been through, but it's the most recent Ice Age, so we commonly refer to it as the Ice Age. Really, we should probably use the term Ice Ages. Louis Agassiz is basically the scientist who popularized the idea of an ice age. Next slide shows glacial rebound. Basically the idea that glaciers are heavy, and when you build them up on top of continents, it causes the continental crust to sink down, the mantle underneath flows away. When the weight of the glacier is removed by it melting away, suddenly that weight is lifted off the continent pops back up again. The next slide after that is basically showing sea level rise, and this is looking at sea level rise over the past 20,000 years, and you can see that basically sea level was at its lowest around 18,000 years ago. This is called the last glacial maximum, and sea level's been rising since, and it's risen a lot more up until about 6,000 years ago, and it's been relatively stable for the past 6,000 years, the same 6,000 years, by the way, that our civilization developed. Next slide after that shows two pictures, one of Alaska and Siberia, and then a lower image of Indonesia. Basically, the Alaska-Siberia picture is showing that when you lower sea level by the amount, about 100 meters that it was at 18,000 years ago, you end up getting a situation where Alaska and Siberia are one landmass. Basically, the ocean in between them in the Bering Strait is very shallow. It's shallower than 100 meters. So when sea level drops by 100 meters, suddenly there's this 1,000-mile wide landmass that connects North America to Eurasia. And this was a major conduit for bringing species back and forth between the two continents. Most importantly, humans. So Native Americans crossed the Bering Strait land bridge sometime in the past 20,000 years and colonized the rest of America. The lower part of that image, the part about Indonesia, shows two clusters of islands in Indonesia, basically those that have Asian species on them and those that have Australian species on them. And the line that divides the two is called the Wallace Line. It basically represents a strait of water that was too deep and wasn't yet revealed at the time of the last glaciation. So sea level dropped by 100 meters, but this strait was deeper than 100 meters, which meant there was no mixing across that line. It's named for the biologist Alfred Russel Wallace, who first described it. He was a co-discoverer of evolution with Charles Darwin. But essentially, east of the Wallace Line, you've got Australian species. West of the Wallace Line, you've got Asian species. That's the big idea there. The next slide after that shows glacial Lake Missoula in Montana. This is a large lake that formed when the Clark Fork River was dammed by a big glacier that came down out of Canada during the Ice Age. Water backed up behind that glacier. It carved a series of shorelines in the hillsides above Missoula, Montana, and those shorelines are still visible today if you ever go to Missoula. There's a great episode of the TV program Nova called Mystery of the Megaflood, which I highly recommend watching, about that event. The glacial lake eventually floated its glacial dam, because ice floats, of course. If you get enough water behind a dam made of ice, the dam's going to float out of the way. And then all the lake drained in a catastrophic flood that went across eastern Washington state, creating an area called the Channeled Scab Lands. So I just wanted to point that out, kind of a neat tie-in with the glacial cycles in the Ice Age. So the final slides in the lecture basically deal with why we get ice ages, why ice ages occur. And we've had them in the past due to plate tectonics positioning continents over the pole. That's what's shown in the first image where it says glaciation's past. Why? Reason number one, plate tectonics. So if plate tectonics moves continents into the cold regions of the Earth, that allows them to build up lots of ice, and you end up getting an ice age triggered that way. Currently, there are no continents over the North Pole, but there is a continent over the South Pole, and of course, it has a big ice sheet sitting on top of it. So the other interesting thing about why we get ice ages is why they wax and wane. There's very good evidence that the ice age in North America basically advanced and retreated and advanced and retreated, advanced and retreated, advanced and retreated. And that's just the evidence on land. Basically, that indicates that there were at least 4 cycles of advance and retreat. And when you look into the oceans, in the areas that weren't being re-bulldozed by glaciers every few thousand years, the oceans actually record up to about 40 of these independent cycles where glaciers were advancing and retreating. So the next 3 slides that are all dark in color talk about milankovitch cycles. These are basically orbital cycles of the Earth's position relative to the Sun and how much energy the Earth is getting from the Sun. The Sun itself seems to have a relatively constant energy output. It varies on a very short cycle, an 11-year cycle that's correlated with the sunspots. But the Earth, relative to the Sun, has some more interesting variations. One variation is that as the Earth orbits the Sun, sometimes it orbits it in a relatively close to a perfect circle, and sometimes it's more of an elliptical orbit. And this is called the eccentricity of the orbit. The other thing is that as the Earth rotates around, basically the angle of its rotation shifts. So let's see, I guess I could use my water bottle here. Let's pretend this is the planet Earth. As it's rotating around, it's got this axis of rotation. And that axis could be something like this, or it could be something more like this. All right? So the position of the axis relative to the plane that the Earth is orbiting in, that actually varies over time. And it varies between a minimum of about 22 degrees and a maximum of about 24.5 degrees. So that's called obliquity, and it's the second of the milankovitch forcings on the climate. And then the last aspect is what's called precession of the equinoxes, or more prosaically, it's called wobble. And the idea there is that the axis of spin actually itself rotates around over time. So you can think of this like a spinning top. You know, when a top is spinning, it's spinning very rapidly, but then as it slows down, it begins to wobble around. All right, it's the same thing. The planet Earth's axis of rotation actually wobbles over time. And that basically means that sometimes during the shortest day of the year, the northern hemisphere is pointed away from the Sun, and sometimes during the shortest day of the year, it's in a warmer position. So you end up getting basically different amounts of heat absorbed by the northern continents. And the last 2 images in the slideshow basically take a look at these 3, the eccentricity, the tilt of the Earth's axis, and then the precession of the equinoxes. And when you stack all 3 of those effects together, which each have a little bit of warmth associated with them or a little bit of cold, they can either cancel one another out or they can amplify one another's effects. So if you look at the combined picture down at the bottom of the last slide, you'll see this wiggle, and sometimes that wiggle has more pronounced ups and downs. So basically when it's up, that indicates it's warm. When it's down, that indicates it's cold, and you might get an ice advance. When we go and we look at these cycles of what the Earth is doing relative to the Sun, these milankovitch cycles, we find that they are in fact correlated with what we observe in the geologic record on the basis of glacial ice cores and also deep sea sediment cores. So as we see this back and forth in terms of the amount of heat the Earth is getting from the Sun, we also see this back and forth in terms of whether we have glaciers or not, a back and forth in terms of whether it's cold or whether it's warm. So basically the bottom line here is that we think the reason that the ice ages have had this sort of waxing and waning character to them is because of these milankovitch cycles, these slight changes in the position and orientation of the Earth relative to the Sun. So that's just a quick wrap up there of that class. Thanks very much, and sorry we didn't get to finish during class.